why reversible engines are the maximum efficiency engines, but that kind of like just falls like a ripe apple out of this idea of chained together power plants. So I have a steam power plant. If I just had like one of these, and as a caveat on this, I have no idea how steam power plants actually really work, aside from the fact that heat makes steam and the steam turns a turbine. And I guess there are two different sets of turbines, and the steam output from one is the input to the other. So I would start with this picture. So what I have is, we'll call it TS for super hot, because we're going to need 3 of them. And just normal engine stuff happens. So we'll call this E1 for engine 1, and it's spitting out work 1, and it has Q, we'll just do 1, 2, and 3, and then we'll call this Q2. So this is just like one plain old ordinary engine, but what you're doing is you're basically capturing this. So imagine that you put like a little device on your car's exhaust and use that to, capture that heat and use it to run a little engine. You have Q2 and W2, and we'll call this Q3. And we'll call this TC because really that is hot. So the only extra thing that's in here is that somebody has to tell you what the temperature of the heat from which this heat is being drawn, i.e. the exhaust temperature of engine 1. And we'll call this like TH for hot. It's not super hot, it's not cold. So this is the picture, and essentially what's going on is the entire work that the entire engine is doing is work 1 plus work 2. And aside from that, like this comes up a lot in thermo problems with cycles and things like this, is that you basically treat this like a Sudoku problem where you like fill in all of the things that you can until you finally have your answer. So for instance, for work 1, this is what I would do. So work 1, I have, I'm told that this thing has 65% of the Carnot efficiency. So that's 0.65 times 1 minus, okay, what ratio of temperatures for E1? May or may not be like sneaky backhanded quiz review.
It should be the temperature, the colder temperature over the hotter temperature.
Yeah, and so for engine 1, that would be sort of unexpectedly TH over TS, so T hot over T super hot. And then likewise E2, because that's also 65% of the Carnot efficiency or max efficiency, that would be 1 minus TC over TH. Okay, so you have these two things. Great, what does that tell me about work? Well, by definition, what's true about the efficiency, for instance, of E1? Also backhanded quiz review. So just the original and most useful definition of efficiency. And if you ever think you're gonna guess wrong, like what it kind of depends on, because this is a heat engine, basically you're asking how good it is based on the input. Notice that it's never 65% or 0.65. It's not going to be greater than 1, so don't violate any laws of thermodynamics. Of Q hot or work, what needs to be on the numerator?
Work.
Yeah, so work 1 over, in our diagram, Q1. And then likewise, E2 is work 2 over Q2. So basically you have these numerically because you were given the efficiencies of the engine and the temperatures at which they operate. And then what you can do is you can use that to figure out the works in kind of the backhanded way of finding the efficiency. Okay, so finally, and I think this is the thing that, this, honestly, this one, it's kind of too late now and don't hate me. If I had, you kind of like look at the problems and then you assign them. This is like super brittle where none of the calculations are hard. It's just there are a lot of them. And if you make a little mistake, you just keep typing stuff into the computer and it doesn't say yes because you used percent instead of a fraction. So this is one of those problems. I would make sure I do all the little parts of it correctly. Ultimately though, what you end up with is you've got to finally find the amount of coal and the amount of water, which turns into, and this I think is what kind of gets people the last step, is it turns into a units problem where the heat of combustion of coal is something, which essentially means the joules per mass is 2.8 times 10 to the 7 joules per kilogram. So basically, if I wanted to know actual Q, whether it be Q1 or Q2, and it is Q1, you want to know the coal is being burned in order to make Q1. Q1 times this, sorry, do that backwards. I don't know why my eraser is messing up. There you go. So the question ultimately asks for how much coal per time, right? At what rate coal must be burned. So what you have is this, you have heat per mass, and M is always, or sorry, Q is always kind of a delta, it's a heat flow, so that's really per mass, so we'll call it delta M. What you want ultimately is delta M over delta T. So you want something in kilograms per second. Okay, and you guys are knee deep in the problem already. What I can do is I can tell you within the randomized numbers, if you get something like on the order of 100, like maybe 200 to 50 or something like that is the range. So this, and they don't tell you the units, I don't think explicitly. So, assuming this is SI is correct. If you get this in between 50 and 200 kilograms per second, it's worth plugging it in. Otherwise, you may have made a mistake. Okay, so that's part A. Part B, we're going to cool the plant with water. And what I want is the water to increase no more than 4.5 degrees Celsius. So this is another rate problem. You also want delta M over delta T. And now they're telling you per hour. So you got to be careful about those units. And this becomes a calorimetry problem. So you have the waste heat. So now the heat that you care about is all the way at the end of the chain of engines. So this is being used. It's this heat. So basically we want to mitigate this heat, the QC, at the end of the chain. So QC just turns into a normal water calorimetry problem. So what you want is C of water delta M over delta T times 4.5 degrees C. It's a delta, so we don't care about Celsius or Kelvin. This honestly would be like a really good mini project question and less so much like a all or nothing homework question, but there it is.
And then how do you get QC?
Yeah, so QC is one of so the way that I would do this is starting all the way at the beginning of this picture. There's a great picture. Is you have T super hot, Q1, Q2, QC, work 1, work 2. I don't know which one you're going to figure out first because you could solve the efficiency a little bit differently, but you can still conserve energy. And if I conserve energy and I look at all the heat going in and all the heat going out, so think about this maybe like, you remember the current junction problems from doing circuits. What is the energy that's leaving the system, like, or entering the system, like the whole system of engines? The only thing that's going in is which Q or W?
Q1.
Q1. But then what three things do I have leaving?
Work 1, work 2, and QC.
Yeah. So in between that and the efficiencies, so you have, really briefly, you have this, you have like E1 is defined as work 1 over Q1. That's great. So you can eliminate that because you actually have a number for this. And likewise, E2 is equal to work 2 over Q2. Not super helpful in the form it is now, but you could also rephrase it in terms of QC through the first law. So that's the first part before even again, none of the individual steps are fundamentally new or different. It's just there's a lot of stuff going on in this problem. And what I would do is I would start with this picture and then just come up with the numbers for them. And then once you have QC, honestly, both of these questions are just like take QC and figure out the rate of coal, or Q1 and figure out the rate of coal, and QC and figure out the rate of water to flow past it and mitigate this much energy.
Okay, thank you.
Yep. Yeah, and again, the all or nothing grading kind of annoying, but I will say that you've gotten everything that you would get out of the problem if you try it 6 times and don't get the point. And again, I'm considering all this when I go through the final grades. So, good. Any other homework or mini project questions? Okay, because we're here and this is like really important, you would spend at least a few minutes marveling at how awesome this is in like a full class dedicated to thermo. This is the proof that reversible engines are maximally efficient. And it doesn't require any detailed knowledge of the Carnot cycle, which the book kind of makes it seem like it does. So the Carnot efficiency is the maximum efficiency. It turns out the proof is if it's reversible, it's maximally efficient. So let's assume I have one that's better than a reversible engine. And we'll call it a super engine. And what the super engine does, so here's my boring max efficiency engine. So this is a Carnot cycle. And again, it's not important that it's adiabats and isotherms. And what it does is it extracts Q hot and it dumps out Q cold, and it does some amount of work. So by saying I can do better than that, what that means is that I have this super engine that delivers work plus delta. There's a possibility I get the delta wrong. Yeah, so basically it extracts a little bit of extra heat and does a little bit of extra work, right? So this is more efficient because work has increased. And work is smaller anyway. So if you think about the fraction, you know, the smaller number getting bigger by the same amount as the bigger number means the fraction gets bigger. So this is a more efficient engine. Okay, can anybody think of a way to power the entire universe for free with my two engines, one of which is reversible and the other one is more efficient than the reversible engine? What do I do with the reversible engine? And again, when you see this, it's like, voila, you've proved one of the most important theorems in physics by doodling, which is like, you know, fairly impressive if you think about it. Okay, what would happen if I reverse the reversible engine and turned it into a fridge? What would have to be true about the work? Am I extracting work from that, or what do I have to do to the work in the Carnot cycle? Instead of pulling work out, I would actually have to do what?
Input.
Yeah, so I'd have to provide work W. Okay, can anybody think of a really clever way of providing work W to the Carnot cycle where I basically get energy for free from the universe?
From the super engine.
Exactly. So what you do is you split the super engine into two parts. There's the delta you get for free, and then the W you dump into the reversible engine. So it gets a little bit messy with the garbage drawing, but this is essentially like if you put a magic bag over this whole thing, this is the engine that you get. Okay, you spit out or you pull in QH plus delta, but then you return QH. So net you have delta in. Down here, you spit out QC, but then you pull QC back in, so that's nothing. And then in the work side, I pull out W plus delta, but I use W, so I'm left with that. So in total, what this chaining of engines together, it turns 100% of work into heat. It's perfectly efficient. You know, supposedly in the fever dreams of Nikola Tesla, he did this, but you know, this doodle probably indicates he didn't. Okay. So any questions about that stuff?
I don't have any questions on that, but can we go over one thing on the mini project?
Yep.
It's for the heat flow from A to B, or number one.
Let's see, maybe bring it up. So Windows always like shames me for having 9 million windows open. Okay, can you guys see the doc? Oh shit, this is, yeah. Sorry, brought up the wrong one. For which one?
The heat flow from A to B. So D, part D.
Yeah, so the heat flows, you know, maybe this is like the theme for today is this is like a Sudoku problem. This is, I think, the easiest and most universal way of doing all of the heats, with the exception of the isotherm, where you just realize that if the temperature of the gas tells you the internal energy uniquely, if the temperature doesn't change, the internal energy doesn't change, so W equals Q. That one, you know, kind of quickly going through it, you get for free. But the rest, I would do this. I think this is the easiest and most universal way of solving the heat problems is, let's say that I have point A and I have point B. And what you guys basically found already is all of the information to describe these points. So monatomic ideal gas means that the internal energy at, I'm picking on point A, but it could be any point, is 3/2 nRTA. So what I know is at every single point, I know the internal energy. Likewise, I know that UV is 3/2 nRTB. So I know the energy change, total internal energy change from A to B, which would be final minus initial UA minus UB. And if I like doing things formally because I'm more of a scientist than an engineer, in my heart of hearts, if you put in numbers, that's, you know, it's a preference. But whatever, I can use that to figure out the energy change in between any 2 points at all. Well, you've already figured out the works through the geometry of the areas under the curve, et cetera. So what do I know about delta U for any process whatsoever by the third law? Or sorry, first law. Getting ahead of myself.
It's equal to the heat flow minus the work.
Right. So you can figure out this, and you already know that. So I think the easiest way of solving these generically, because you already have work, since you already computed the work by finding the areas, all you have to do is plug in 3/2 nRT for all of these. And then you have the total amount of joules, like all of the energy in the gas. And then what you can just do for each of them is say that, you know, QAB, for instance, equals delta UAB plus WAB. And you know it, you know, simple algebra problem, you got it. The exception, well, it's not even an exception. You don't have to explicitly compute the change in internal energy for the gas for the isotherm. Just realize that what this says is if I move along a line of constant temperature, that's 0. So Q equals W for the last one, for D to A. Any other questions about the?
Actually, for part C of this problem where you're finding the work, that made sense to me, except that every time I calculated the work going from A to B, before I was calculating the work, I was trying to calculate what the difference in the volumes were between A to B. And I was coming up with a volume for B that was less than A, which to me didn't make sense because
Because of the picture?
Yeah.
Yeah. So let's see. There's a little bit of a sidebar. I kind of forget what you're told. You're told that like PA is half a megapascal, and you're told that VA is 1 liter, or 1 × 10⁻³ meters cubed. I'm going to keep everything in SI because I don't trust myself. And then TA is 400 Kelvin. And then you know N, it's less than 1, so we'll just say that. And you're told, likewise, PC, I'm not going to write them, but it's a V. And you're told that the B and C are connected on isobar, right? So PC equals PB. Yeah, I gotta kind of toggle back and forth and see which things actually tell you. Okay, so they tell you TB, they tell you PB, and you know the moles of the ideal gas. Okay, so that's actually all you need. So you know PB is 1 × 10⁶ pascals. You know that TB is 960 K. and you know n. So you should have PB VB equals NR TB, or VB equals NR TB over PB. So let's make sure that nothing crazy happens. The pressure in between A and B doubles, and the temperature in between A and B more than doubles, so this should be bigger. So the numerator has more than doubled from 400 to 960, but the denominator has only doubled.
Okay, it might be a problem with my my moles then. I'll have to recheck that.
Yeah. Again, the moles I can tell you, and again, in general, as always, I'm happy to look at rough drafts. Should be less than 1. And this is the unit that you should put in for volume if you want to get moles. If you use liters once and then meters cubed for another one, you might end up with like a different answer. But I think this is the easiest way of just finding VB. And it should be halfway in between VA and VC. So somewhere in like the 1.25 range. 1.25 liters. Good. Any other questions about that or anything else? Okay, so I guess we'll just get to the atomic spectra and the Bohr series on Monday, which is fine. I just want to do the last part of the tiny primer on quantum mechanics. That again, this is like kind of all you really need. Again, there's so much in the richness of quantum mechanical behavior. The idea in general is that everything kind of has this dual nature. Light acts like waves and particles. The particles are called photons. And you know, that's kind of at the, oops. Yeah, I don't think it likes the fact that I'm sharing 2 screens. Let me start. Yeah, there's one tiny bit of mastering physics on the spectra problems. Is that visible to you guys? I think I saw some people working on it.
Yeah.
Yeah. Yeah, I don't know how accurate the times are, but it said it was slated to take an hour or something like that. So they're just nothing spooky, just literally plug in questions, I think. Okay. All right, so this should be better. Okay. Everything has a wave and particle nature. The 2 bits that we haven't covered are the fact that a photon energy, so this is it, like red light only comes in chunks of Planck's constant times the frequency of red light. So, you know, think about it like gold atoms. You know, you can split a sheet of gold smaller and smaller and smaller until there's only 1 atom of gold. Likewise, you can break red light up into smaller and smaller pieces until there's just 1 packet of red light, and this is its energy. Likewise, you could do the same thing with green, or gamma rays are a valid form of energy. So this is where we ended. The second part, and this is the part that all the like spooky woo-woo stuff in popular culture kind of refers to, is that matter acts like waves. So if you put a stream of electrons through a double slit experiment, you get an interference pattern the same way you would do with light, which was kind of our smoking gun that light has a wave nature after doing all of geometric optics. And the thing that's like triple spooky about this is you can turn the beam of electrons down until there's only 1 electron coming through at a time, and you would still see this interference pattern build up on the screen. So it's literally the electron interfering with itself, which, you know, it just sounds bizarre in just human languages. It's, there's a full theory. We understand at least how to use it to make predictions. But this is the important second piece. So this is all you need to know about the quantum mechanical behavior of matter for this class. Is this guy, Louis de Broglie, this is his PhD thesis. He said that the wavelength of matter is given by Planck's constant, the same one divided by momentum, or mv. And so the reason you don't see this in everyday life is because Planck's constant is really, really, really small. And the mass of like bulk matter is generally pretty big. And even something like nitrogen, you guys know that that's like maybe 400 meters per second. So this is a tiny wavelength and you have to work really hard to isolate it. So yeah, at this point, I'll just do this problem, let you guys get set up for the quiz. And then we'll do the actual mechanics of computing stuff with the Bohr model on Monday for the first half at least. Okay, so this is how you'd compute the de Broglie wavelength. It's literally momentum. So I find the momentum of this thing. That is the mass, whoops. That is the mass of the electron if we're talking about this electron double slit experiment. And then the velocity of electrons. You're even doing a really good job if you get them down to 8 kilometers per second. So SI units, 9.11 times 10 to the minus 31st kilograms times 8,000 meters per second. And then I would take that and I would divide by Planck's constant. And before I write the number, any guesses about what the wavelength of this rather slow, and you don't get less massive than the electron really. So this is the smallest mass that I can really get out of the commonly available fundamental particles. So at least, kind of internally make a guess if this is meters or kilograms or sorry, kilometers or meters or millimeters or submillimeters. Yeah, we'll round it off. So even with that, we can't even get to the wavelengths of visible light. So your dreams of having like a diffraction pattern from electrons using an old cathode ray tube in a human hair are basically dashed. That would be hard to do anyway because the electrons, if they weren't in vacuum, would, find a positive charge to hang out with. But so we don't really see this too much. However, the evidence of its behavior shows up in all of the atomic spectra. So we've been looking at these chunky atomic spectra for the entire quarter, and the story behind them is that they're essentially standing waves. So the whole point of musical instruments is that you can only have certain allowed wavelengths if you fix a wave at like the bridge and the fret. And I don't know if you guys did the standing wave lab. I think you may have even done the sound standing wave lab, which is kind of terrible to hear all those beating noises. But you're familiar with this idea. This is basically what's going on in an atom. So in an atom, because the electrons have this wave nature, is they're making like circular standing waves. And to get from one to another, basically I'm adding one extra lump. So I can quantize the orbitals, it's what is called, and they can only appear in certain allowed 2 pi r equals n lambda. This should look really familiar. So I basically count the lumps, and that's the circumference. So that's the shortest story possible about the Bohr model. What we'll do is basically go through the nomenclature of the Bohr atom formulas and the Rydberg formula that would show up on the MCATs, because there's just a little bit of, it's use this formula, but know what the hell they're talking about with these different series names. So we'll do that on Monday. And yeah, we'll start there. So basically what that has to do with these formulas, this idea of quantization and how to use them.